So I guess I'll start with just reviewing a couple of things from the very end of my talk from yesterday. Oh, and I think I want to introduce a bit of notation. That's not really legible. Okay. So let xg be the set of pairs that was sort of omnipresent in my talk yesterday. The set of pairs where C is a unipotent class and E is an irreducible G equivariant local system. And just to remind you that this is also something you can identify with the set of simple equivariant perverse sheaves on the unipotent variety. Okay. So maybe I'll remind you about the restriction and induction functors that I introduced just at the end of my talk. So if you have a parabolic subgroup like this, so V was the unipotent radical of that. Then I had the inclusion map IP from P to G, and the projection map from P to the Levy factor called QP. And there's the restriction functor, which was defined to be you pull back along IP. So you start with a sheaf on G, pull back along this map to get a sheaf on the parabolic, then push forward along this map to get a sheaf on the Levy. And for the induction functor, I'll write down the formula and I'll draw a little diagram as well. So for the induction functor, starting from a sheaf on the Levy, you pull back along QP, except it's the Schrieg pullback, and then you do this G cross P construction that I described yesterday, and that gets you to a sheaf on G cross upper P P. And then that maps to G, so then the last step is push forward along that. So let me maybe draw a little diagram that shows where some of these things are supported. So let's say you take a pair C1, E1, in XL. So that means on the unipotent variety for the Levy, I'm taking a unipotent class and an irreducible local system on that. And so I just want to draw a picture of sort of what comes up when you compute this induction thing. So instead of drawing all of G cross upper P with P, well, the perverse sheaf that I want to induce is supported on the closure of one unipotent class, which is contained in the unipotent variety of L, and which is contained in L. So when I apply QP upper Schrieg to it, this is supported on this variety. So on the closure of C1 times V, which is contained in this parabolic. And so instead of forming G cross upper P with P, I could just look at a piece of it. And then this variety maps down to, well, I could put G at the bottom here, but I mean, what is this map? You take an element in here, which is an element in the parabolic, and you just and you act on it by conjugation by whatever element you have in G over here. Well, everything here is unipotent, so when you act on it by conjugation, of course, you're only going to get unipotent things. So instead of writing G here, I mean, this map pi is going to take values in the unipotent variety. So you end up with something supported on UP. So when you do the induction procedure, so I guess let's see. So QP upper Schrieg of IC C1 E1 lives on this space, and then you apply a G cross upper P and you get something on this big space, and then you push down and then you get something on the unipotent variety. So yeah, so I guess the thing I want to write down, which I mean the observation I want to make is that if you start with one of these pairs in XL, when you apply the induction functor to it, you get something supported on the unipotent variety. And there was a special case of this, which was the exercise I wrote down at the very end of my talk on Wednesday, which was this case. So if you induce from the torus, well, what's xt? The unipotent variety of a torus is a single point. It's just the identity element. And it's easy to understand the category of local systems on a point. There aren't a lot of choices there. So anyway, there's the trivial unipotent class in the torus and the constant local system on that. And the exercise was to prove that's the Springer sheaf. And well, to prove it, this diagram is what you have to write down. In the special case where you take the torus and the Borel, this variety up here is just exactly what I called U tilde yesterday. And let me just remind you what the rest of, what the main fact from yesterday's talk was. You decompose the Springer sheaf with the sum over xg. So you take ICCE tensored with some multiplicity space. And these multiplicity spaces, they're either 0, or if they're not 0, they carry a natural action of the Weil group, and the ones that are not 0 are irreducible W representations. And every irreducible W representation occurs once. And so the statement of the Springer correspondence was that, well, by labeling these simple perverse sheaves by representations of the Weil group, well, what you get is you get a bijection between irreducible representations of W and simple summands of the Springer sheaf. And that's some subset of xg. And the problem that that I want to address today is how do you account for the missing stuff in xg, the pairs that don't arise in the image of this map. And just to have something concrete to keep in mind, I'll fill in this example more a bit later in the talk. But for SL4, you can write down all the unipotent classes that are labeled by partitions of 4, and there are 5 of them. And then you can sit down and compute what the A groups are. And they're all pretty small. One of them is Z mod 4, and there's another that's there are 2 others that are Z mod 2, and then the rest are trivial. Anyway, what happens is that xg in this case has 9 elements, but the number of irreducible representations of the symmetric group on 4 letters is 5. It's the number of partitions of 4. So there are 4 missing things. So there are 4 missing pairs. So later we'll see what to do about those. Okay. So, so the idea is, well, the idea is something that you would have anticipated because I've introduced functors called induction and restriction. So the idea is to develop some kind of Harishchandra theory for perverse sheaves on the unipotent variety. So I'm going to tell you a list of facts, and some of these are going to be sort of out of historical order, and in some cases a little bit out of logical order, but hopefully slightly better for understanding order. So anyway, so here's the very first fact that we need. I think I'm going to try to number my statements consistently with yesterday. So I think the last numbered statement yesterday was 5. Anyway, so theorem 6 is this. So we need some basic facts about induction and restriction. So the first thing is that restriction and induction this is an adjoint pair. This part, it's basically obvious. I mean, yeah. I mean, you know, this is just unwinding some basic facts about sheaf functors. The next part is really not obvious. So these restriction and induction functors, I define them as functors on equivariant derived categories. So what's not at all obvious is that if you just plug in perverse sheaves on the unipotent variety, they give you exact functors. So both of them are exact. So if you plug in a perverse sheaf on the unipotent variety of L and you induce it, you get a perverse sheaf here. And if you restrict a perverse sheaf on the unipotent variety of G, you get a perverse sheaf here. And the last statement is that they take semi-simple perverse sheaves to semi-simple perverse sheaves. So I'll tell you I'll tell you some of the ingredients that go into this. So for the exactness, this is some. I mean, the exactness statement is well, it's morally the same kind of statement as a statement from yesterday, which I think I called theorem 4, which said that the Springer sheaf is a perverse sheaf. And Victor Ginsburg had a semi-smallness theorem in his talk, and that was also this flavor statement. And Victor Ginsburg actually he gave what I thought was a very slick proof of semi-smallness. So the argument that he gave, you could use that for theorem 4b, but I think not for theorem 4a, which was a slightly stronger statement. And anyway, I'm saying a lot of numbers, so I'll write some things on the board in a bit when we need a sort of a more careful version of these things. But for right now, so for the exactness, what you can do is you can. It's not too hard to get a one-sided exactness statement. By doing dimension calculations. I mean, yesterday I told you that theorem 4 really comes down to dimension calculations. So you can do a one-sided exactness statement by doing dimension calculations, like in theorem 4b from yesterday. And you can guess which way the one-sided thing should be. So in that adjoint pair, well, the left adjoint should be right exact, and the right adjoint should be left exact. I mean, if you prove a one-sided exactness statement for one of them, it's automatic for the other one. And then to get them to be exact on both sides, this was not Lustig's original proof. By the way, almost everything in my talk today is due to Lustig. But I think a sort of fancier, a shorter, more modern argument is to use Braden's theory of hyperbolic localization. So I won't go into a lot of detail about what that is, but it's the main thing it does for you is that it tells you that that if you could write down some formulas, well, you can write down a formula for a functor like restriction, but with the stars and the shrieks reversed. And that kind of functor is going to have the opposite exactness properties. And Braden's work tells you that it's actually the same functor. So it's kind of, it lets you skip doing a lot of hard work. And then for semi-simplicity, there's a, well, I'll tell you two reasons for this. So for induction, the reason it takes semi-simple things to semi-simple things is the decomposition theorem. And for restriction, it's Braden again. One thing that Braden proves when, as part of his work showing that these two opposite-looking functors are actually isomorphic, is that they preserve weights. And they take pure objects to pure objects. So that's exactly the kind of thing that's going on in the decomposition theorem as well. So there's a I want to make a little side note here. There's sort of a silly reason. If you spend a lot of time playing with perverse sheaves on the unipotent variety, then you know an obvious reason why these functors are exact. Or sorry, take semi-simple objects to semi-simple objects, and that's because the categories are semi-simple. Every object is semi-simple. So this this looks a bit silly, but I think actually this is a better. This is sort of a better moral reason for it. I think somehow, I guess in my mind, proving that this category is semi-simple is somehow it's a kind of computational statement, and it's not very conceptual. But these are somehow, well, there's some big machinery, but it's machinery that's sort of widely used and widely available, and it's sort of it's easy to see that that's the reason for it. I guess, yeah. Anyway, I guess I think in my mind this is the reason, and this is somehow a nice extra fact. Okay. Okay. So. So now that we have induction and restriction, we need to start inducing and restricting something. So there's one induction statement written on the board already, the Springer sheaf. So let's try and write down some more things. The thing that's implicit in this sentence is that you should sort of look for things that can't arise by induction from anything smaller, and call those things cuspidal, and then those should play sort of a key role in the theory. So here's the definition. So pair CE in XG is called cuspidal if its restriction to any proper levy is 0. So if you take any parabolic which is distinct from G, then that should be 0. So here's the next theorem, theorem 7. So this is I'll call this the induction series theorem. So the induction series theorem is going to say that every pair comes from or arises as induction from a cuspidal thing in a unique way. So for every CE in XG, there exists a triple L C naught E naught, where so of course L is a levy, C naught E naught is a pair in XL, and it's a cuspidal pair for the levy. And this triple is it's unique up to G conjugacy, so it's as unique as you could expect it to be. And then such that, so the such that part is that the perverse sheaf labeled by this pair, so IC CE, is a summand of the thing you get by inducing this. When you induce this cuspidal pair. Okay. So the existence part of this theorem is basically obvious. I mean, it's obvious using the fact that restriction and induction are adjoint. So if you have something that doesn't occur as a summand of any induced thing, then by adjunction, its restriction to every levy must be 0. So it's cuspidal. Oh yeah, right. So just to make it clear, it's possible. I mean, CE itself might be cuspidal. And in that case, the triple is G and then just CE. So yeah. So the existence is obvious. And the uniqueness, probably the shortest way to say this is that you use a kind of Mackey formula, which relates sort of restriction and induction from different levies. So something like if you induce from one levy and restrict to a different one, then you want to write that in terms of restricting to various smaller levies and then inducing from them. So I think that, well, anyway, I'm not really going to say anything more about the proof of that. But anyway, this theorem gives you a way to split up XG in a way that's labeled by these triples, L, C naught, E naught. So I'm going to write the L, C naught, E naught as a superscript there. So the thing on the right there is just defined to be the set of simple summands of what you get by inducing this cuspidal one from L to G. Okay. So the other part of developing a Harshchandra theory is that, well, you want to be able to say something about what the pieces in these. So these, I guess these subsets of XG, that's what I want to call induction series. So we want to somehow parameterize the things in each piece of the right-hand side here. so one piece of star is what we talked about on Wednesday. It's the induction series corresponding to the torus and the trivial unipotent class and the constant local system on that. And this is well, simple sum ends of the Springer sheaf. So we've already seen this, and that's in bijection. I mean, the Springer correspondence says that's in bijection with the representations of W. So here's theorem 8. Okay, so theorem 8 says that for every one of these triples, the induction series is naturally in bijection with irreducible representations of something that looks just like a Weil group. It's the normalizer of the levy that you induced from mod that levy. So this kind of thing, sometimes it's called a relative Weil group. So I want to say a little bit about the proof of this. It has a lot of the ingredients. I mean, somehow the ingredients in the proof of this, they're fancier versions of of all the statements I wrote on the board yesterday. In some cases, the proofs are really similar. In other cases, they really take a lot more work. So let me write down some notation here. Well, we have our parabolic. I mean, that notation is the same throughout. I want to let Z naught of L be this is the connected component of the center of L. And then I want to define something called Z naught L reg. And what you should think of is, in the case where the levy is a torus, this is going to be the set of regular semi-simple elements in the torus. So, but for a general levy, I want to take elements in the center of the levy such that the centralizer in G of that, or at least the connected component of the centralizer in G of that, is contained in the levy. So somehow having too big a centralizer is a closed property, and we want to get rid of those. Okay. Okay, so here's the main diagram for today. It's going to reduce to the main diagram from Wednesday if the levy is a torus. So the main diagram looks like this. So the leftmost part is this. So this arrow right here, I drew this. I guess I already erased that. I drew this on the very first board when I was talking about what induction actually does. So that's a piece of it. Oh, sorry. I think I wanted to introduce a bit more notation. So let's let sigma be Z naught of L times C naught. So this is contained in the levy, but it's not. It doesn't have just unipotent elements anymore. It has these central elements in it as well. And then sigma reg is Z naught of L reg times C naught. Okay, so the middle piece in this diagram is G cross upper P sigma bar V, and this maps down to G. And then the right-hand side is G cross upper P sigma reg V. And then what goes down here, I'm just going to write g dot sigma reg. So sigma reg is some subset of the levy, and then I want to just take all g conjugates of that. And I'm omitting the v here. You could put the v if you want, but you actually it turns out that these are just equal. So So I know that there's a lot more notation here than there was yesterday, but everything has sort of the same flavor. So so I'll tell you sort of the main steps of the argument. So here are the steps. So the first thing is that this space on the upper right here, I can write down a description of it that doesn't have p in it anymore, that just has the levy. So this is isomorphic to the set of pairs g comma xl in g plus g mod l, such that x inverse gx is in sigma reg. So yesterday we had something exactly like this, but with basically with regular elements in the torus here, this variety here, it doesn't mention p anymore, and just like with the warm-up trick yesterday and what we did with g tilde rs yesterday, you can make ng of L mod L act on this by multiplication on the right. So ng of L mod L acts on this. And so step 2 is that the sort of regular part of pi is a Galois covering. It's a Galois covering map with whose covering group is what we want it to be. It's ng of L mod L. So last time it was the Weil group. The next step is actually, it's one of the most delicate. So let me write some sheaves on this board. So something we start off with on C naught. I mean, when you're doing the induction thing, you're starting with IC of C naught, E naught. So this is some perverse sheaf supported on C naught bar, and then you do QP upper streak to get something on this piece. Then you expand it to something that's on that lives on this whole variety, and then you push it forward. That's the induction functor. But now what I want to do is I want to enlarge this to something that lives on sigma bar instead. And the enlarged thing is just, well, I'm going to take my local system on C naught and then just the constant sheaf on this center part. So constant sheaf tensor E naught. And what I want to do over here is restrict this local system to this regular part and push it forward. So let L be pi reg star of, well, so let's write down the thing it should be. So it should be G cross upper P of QP upper upper star of the appropriate local system here, which is constant sheaf tensor E naught. So I had a curly L in yesterday's talk, and the formula for L today is, well, it's more complicated, but it plays the same role. Step 3 is to show that the endomorphism ring of pi reg, of L is this group ring. This is probably the most delicate part of this argument. Yesterday, in this part of the diagram, the local system we had up here was just the constant sheaf. and you're pushing forward the constant sheaf along a regular covering, and of course what you get downstairs is then the regular local system for that covering group. Now we're pushing forward something that, well, E naught is something. It's usually not a constant sheaf. And this statement, I mean, you shouldn't be deceived by the easiness of stating it or its similarity to yesterday. It depends on a lot of things. It's not just about the geometry of this map. It depends on sort of, it depends on C naught having certain properties. It depends on E naught having certain properties. So I mean, in order to prove this, you need to understand some constraints on, well, you need to understand what C naught, E naught can be to some extent. Well, but then, then, I mean, step 3 is the hardest part, but then the rest of it is sort of not too bad. So step 4 is to show that what you get in the middle spot here is, so let's see. So this complicated thing in the middle spot, on the one hand, it's equal to, so it's equal to J lower shriek star of L with some shift. I mean, you have to make sure these things are actually perverse. So I think I've probably already made mistakes on the board about shifts, so I think I'm mostly going to ignore them. So on the right-hand side, it's the intermediate extension of the local system you got over here. And on the left-hand side, if you restrict to the unipotent variety, you get the induced sheaf. Okay. So step 5, well, this equality right here tells you about the endomorphism ring of this. It tells you it's the same as that. It's the group ring of NG of L mod L. So C NG of L mod L, this is equal to the endomorphism ring of the local system L, but also of its intermediate extension. And then you restrict to the unipotent variety, and you get a map to the endomorphism ring of this induced object. And this map, this is maybe, this map is an isomorphism. In yesterday's version of this fact, well, yesterday this was the theorem of Borho-McPherson, and the proof involved restricting even further down to the Springer fiber over the identity element. And that kind of trick isn't really available here. So that, I mean, anyway, there's some other argument. And this is, this is tricky. Maybe I still think step 3 is harder than step 5. But anyway, we're almost done now. So the very last step is identical to something we did yesterday. Let's see. So what step are we on? 5. Okay. So step 6 is the induced thing. Well, it's semi-simple. So it's a direct sum of simple perverse sheaves with labeled by multiplicity spaces. Maybe I should label them just to make it clear that this object lives on the levy and this object lives on G. But then that computation of its endomorphism ring tells you that it also has a decomposition that looks like this, where you take irreducible representations of ng of L mod L, and you take some simple object, tensor that irreducible representation, and then you match terms in these two decompositions. Okay, so I guess I erased theorem 7. Well, let me sort of recap what theorem 7 and 8 say together. So together, you get this disjoint union over all these triples, L, C naught, E naught, of irreducible representations of ng of L mod L. And then the statement is that there's a bijection between this and xg, which is the set of pairs that we've been talking about all along. So this is, I guess, the main statement of this talk. So this is the generalized Springer correspondence. So maybe I'll fill in that example that I mentioned a little while ago for SL4. So for SL4, there are 4 pieces in this disjoint union. So there's the ordinary Springer piece, which we already talked about. So that has 5 elements. Then there's only one other non-trivial levy that has a cuspidal pair. And it's a levy of type A1 cross A1. So it's not exactly SL2 cross SL2, but it's rather it's like S of GL2 cross GL2. I mean the thing that looks like SL2 cross SL2 but is a levy. So there's this maybe I'll just call it A1 cross A1. I won't bother with notation for that. What happens in this case, you could sit down and compute ng of L mod L here for this levy, and it's Z mod 2. So it has 2 representations, so you get 2 pieces there. And then what's left is that there are 2 left. So I told you that the total size of this is 9. So there are still 2 missing, and those 2 missing are both cuspidal. So they fit in a piece by themselves on this left-hand side. Okay. Yeah. So if a single L has more than one cuspidal, then there's more than one copy of irreducible representations of ng of L mod L. Yeah. I mean, you could secretly, this group is sort of morally labeled by a triple. It just happens that C naught and E naught, it just happens that the group is independent of C naught and E naught. Yeah, that's true. Yeah. Yeah. This is supposed to be triples up to G conjugacy. So yeah, to get something concrete, you choose a Levy-Niche conjugacy class. But it can happen that a single levy occurs with more than one C naught and E naught. So okay. So I thought I'd say just a little bit about the context for the generalized Springer correspondence. So Lustig's paper in which he established the generalized Springer correspondence, it's sort of part 0 of his series of papers inventing character sheaves. And I'm not going to tell you what character sheaves are, because that could be a mini course or a semester in itself. And they're also, I mean, these were invented in the mid-1980s, and by now there are various more modern approaches to it than what I'm going to describe, and there are sort of more sophisticated perspectives on what they actually are. But anyway, what they are is that there are certain G equivariant perverse sheaves on G, and the goal, so Lustig's main goal in inventing them was, well, I mean, I set up my talk yesterday with the group defined over the complex numbers. But if you instead take a group that's defined over a finite field, the goal that Lustig had in mind was that character sheaves should lead to a way to compute character values of finite Chevalier groups, so things like that. And the perverse sheaves that I've been actually writing on the board, these things that live on the unipotent variety, mostly they are not they aren't character sheaves themselves. So these are usually not character sheaves. The ones on the right side of that diagram, things like this intermediate extension of L, that kind of thing is a character sheaf. But ultimately, what ends up happening is that in this project to compute character values, this arrow sort of hides a lot of complication. But at the end of the arrow, you can more or less come down to the problem of answering the following question. The question of computing stocks of these simple perverse sheaves that do live on the unipotent variety. And this question, maybe I'll keep that main diagram for now. This question has an answer which is really concrete. So there's a so to compute stocks of ICs on U of G, there's something called the Lustig-Shoji algorithm, and it's really an algorithm. So here's what you need to know to run the algorithm. You need explicit knowledge of the generalized Springer correspondence. So you need to know sort of which unipotent classes and which local systems match up with which representations of all those relative Weil groups. And then you need to know some basic representation theory of relative Weyl groups. And I mean just characteristic zero representation theory. You need to know, you need to know things like, well, you need to know fake degrees, and these are things which are sort of really well understood combinatorially. And then the last thing you need to know is how to manipulate matrices. The actual algorithm, it's something where you write down a matrix equation where there are a bunch of entries in the matrices that are unknown, and you sort of keep reminding yourself what it means to multiply matrices, and you realize that you can fill in the entries in the matrices one by one. And the entries that you fill in, they give you the answers. And this is something that you can do on a computer. This part, I think, maybe in principle can also be done on a computer, but it's much more difficult. And there's I think Frank Lübeck is maybe the world's expert on doing this part by computer. And that's much harder than what I described here. Okay, so I guess there's about 10 minutes left. So I think in the remaining time, I want to say a little bit about the Lie algebra version of all these ideas. And I think, so tomorrow I'm going to be talking entirely in the Lie algebra setting. This is and there's a lot which is really identical. So I guess the first thing I need is a bit of notation. So when you work in the Lie algebra, it's n instead of u. So this is the nilpotent cone inside the Lie algebra. The first thing I want to mention, actually, before I say anything else, is that in my setup yesterday, I started with a complex group. So if you work over a field of positive characteristic and that characteristic is bad, then you run into problems. But most of the time, the nilpotent cone in the Lie algebra is isomorphic to the unipotent variety in the group, and the isomorphism is compatible with the G action. So if you're talking about G equivariant perverse sheaves on one or on the other, they're sort of patently equivalent categories. So you could just sort of apply that isomorphism and then transfer everything. But if you don't feel like doing that, the other thing you can do is repeat all the constructions I did yesterday and today in the Lie algebra. So Wednesday's main diagram in the Lie algebra version looks like this. The only thing I'm doing is changing n to u and changing the font of the letter G. This is the diagram from yesterday, and the main point of yesterday was that this right-hand side is a Galois covering whose covering group is the Weyl group, and then you sort of copy everything I said on Wednesday, and if you want to do the generalized Springer correspondence, well, you have to copy the sort of fancier main diagram, which is up on that board over there. The biggest change is that some multiplication signs turn into plus signs. So if you have a parabolic Lie algebra, oops, that was supposed to be an L. So if you have a parabolic Lie algebra, which is a levy plus a nil radical, then I want to let sigma be C naught plus the center of L. And so the picture looks like this. So in place of C naught bar times capital V, it's C naught bar plus lowercase v. And the same kinds of things here. So here there's a sigma reg plus v. So it's, anyway, I mean, there's no difference at all in setting up the diagram. But there is a bit of difference. Well, there's a bit of choice in something at the very last step. So in this main diagram, the equation that lets you transfer information from the right side, where you have a Galois covering, to the left side, where you have some complicated perverse sheaf, is this. It's the fact that when you take this intermediate extension of some local system and you restrict it to the nilpotent cone, you get the induced perverse sheaf. But in the Lie algebra setting, there's a different way you could get from the right side to the left side. And that different way is Fourier transform. So the Lie algebra, of course, is a vector space. And well, there are a couple. I mean, if you like L-adic sheaves on varieties over positive characteristic, then you should add the word Deligne here. So it's either Fourier Deligne or Fourier Sato. So if you're working in the complex setting, you should work with Fourier Sato. And tomorrow I'll definitely need the latter kind. But it's well, what it is, I'm going to denote it with a capital T. So it's an equivalence of categories between the derived category of some vector space and the derived category of its dual vector space. But we're working with a reductive Lie algebra. You can identify it with its dual. So let me just do that kind of silently. The main feature, I mean, one of the main features of the Fourier transform is that it's exact on perverse sheaves. So it gives you an auto-equivalence of G-equivariant perverse sheaves on the Lie algebra to itself. There's a slight lie here. It's not all G-equivariant. You have to insert the word conic somewhere, but I'm just going to forget about that. And it does, it does the kind of things that you think something called Fourier transform ought to do. Like it sends the skyscraper sheaf to the constant sheaf, and vice versa. And maybe I'll erase this. So this is going to be the last thing I want to say. So here's a proposition. The Fourier transform of this intermediate extension of L is the induced sheaf. So that means that we've got two different maps here. So when you take the endomorphism ring of the induced of this intermediate extension, well, that's the thing that brings the relative Weil group into this whole theory. You can either restrict to n to get to the endomorphism ring of the induced sheaf. Or you can apply Fourier transform. And on the left side, well, that's what I had on the board earlier. It's an isomorphism, but it's hard work to prove that it's an isomorphism. This right-hand arrow, well, Fourier transform is an equivalence of categories. So this is automatically an isomorphism. So the main caution here is that these maps are not equal. They differ by the sign character. So if you use Fourier transform on the Lie algebra to construct Springer theory and generalize Springer theory, you'll get a different labeling of perverse sheaves by representations of relative Weyl groups than if you do the restriction way. But just, I mean, the change is just this. Okay, so I guess I should stop.